A freight train can burn through thousands of gallons of diesel hauling cargo across an entire country and still almost never pull over to fill up. And that's not luck. It's a century of deliberate engineering. A single locomotive carries around 5,000 gallons of fuel. A full train often hauls 3 or 4 of them, and yet the whole operation is designed so the fuel stop practically disappears from the schedule. The secret isn't one clever trick. It's 4 of them working together. A tank the size of a swimming pool, physics that barely fights the train, fuel trucks that chase the locomotive down, and the brutal math of what it actually costs to stop 10,000 tons. By the end of this, you'll understand why, in railroading, the cheapest fuel stop is the one you never make. Start with the tank, because the scale of it is hard to picture until you compare it to something familiar. Bolted to the underbelly of a modern road locomotive, slung between the front and rear wheel sets just inches above the rails, is a heavy steel fuel tank that holds close to 5,000 gallons of diesel. To put that in perspective, a typical backyard swimming pool holds somewhere around 15,000 gallons, which means a standard 3-locomotive lash-up is rolling down the track carrying enough fuel to fill that entire pool, all of it moving at 60 miles an hour. And engineers can't just let all that liquid slosh around freely, because a wave of thousands of gallons shifting during a hard stop could actually destabilize the train. So the inside of each tank is divided by steel baffle plates that keep the fuel from surging and keep the weight centered. That massive, carefully engineered reservoir is the foundation everything else is built on. But a big tank only matters if the train can stretch that fuel a long way, and this is where the physics does something almost magical. Because steel wheels roll on steel rails with astonishingly little friction, a fully loaded train fights far less resistance than anything on rubber tires. A 10,000-ton freight train gets somewhere around 3 to 4 miles per gallon, which sounds low until you remember what it is moving. Measured by how far it carries a single ton of cargo, a train is roughly 4 times more efficient than a semi-truck on the highway. That efficiency stretches the train's range to somewhere between 500 and 1,000 miles on a single fill, which is why a road locomotive crossing the continent typically only needs to refuel about twice a week. Hundreds of miles of non-stop movement separate one top off from the next. So the tank is huge and the range is enormous, but 1,000 miles still runs out eventually. Every train eventually hits the bottom of its tank, and this is where most people picture the obvious solution. The train pulls into some giant fuel station, fills up, and rolls on. But that's almost never how it works, and the reason why is the single cleverest idea in the whole system. The railroad doesn't move the train to the fuel, it moves the fuel to the train. It's called direct-to-locomotive fueling, and the logic is beautifully simple. Instead of detouring a 10,000-ton freight train off its route to sit at a central fueling station, specialized tanker trucks, each carrying up to about 7,500 gallons of diesel, drive out and meet the train right where it already is, pulling up alongside the main track or a yard siding. And here's the key. They do not create a new stop. They show up during pauses that were already going to happen anyway, a routine crew change, a safety inspection, a bit of yard sorting. Across North America, this runs as a distributed network of more than 2,000 mapped fueling points, and the trucks pump so fast, over 200 gallons a minute, that a truck can completely refill a locomotive in about the time it takes a fresh crew to climb up into the cab. The truck's arrival is timed to the exact minute the train rolls onto the siding. The train never detours for diesel, because the diesel is already waiting exactly where the train was going to stop anyway. The fuel stop does not vanish, it just hides inside a stop that had to happen regardless. If that idea of bringing the fuel to the moving train sounds modern, it's actually one of the oldest obsessions in railroading, and the steam era had its own wild version of it. Back then, the real bottleneck wasn't coal, it was water. Early steam locomotives drank through their boilers so fast they had to stop for water every 10 or 15 miles. And even as bigger tenders stretched that out to 100 miles or so, those water stops were an unavoidable drag on every timetable. Tiny settlements grew up around these trackside water stops, and they earned a nickname that still survives in the language today: jerkwater towns, named for the act of jerking a leather cord to pull water down from a roadside tank into the locomotive. And railroads hated those stops so much that back in 1870, the New York Central came up with a genuinely audacious fix. They laid quarter-mile-long steel troughs right between the rails, filled to the brim with water, and as a steam locomotive thundered over them at 35 to 45 miles an hour, the firemen would lower a scoop from the tender and let the train's own momentum force water up into the tank, refilling on the fly, at speed, without ever slowing down. Think about how bold that is, refueling a moving train without stopping it. A century and a half ago, diesel engines eventually made those track pans obsolete, but the underlying mission never changed for a second. For more than 100 years, railroads have been chasing the exact same goal: engineer the stop out of existence, and direct-to-locomotive fueling is simply the modern answer to a very old problem. So, why are railroads this fanatical about avoiding a stop? Why not just pull over? How bad can it really be? The answer lives in physics, and it's more punishing than you'd ever guess. A fully loaded freight train can weigh between 10,000 and 20,000 tons. To put that in perspective, a 15,000-ton train has about the same mass as 30 fully loaded passenger jets. Once all that weight is rolling at cruising speed, it becomes an enormous reservoir of stored energy. And every time the train stops, the brakes have to bleed that entire reservoir of momentum away, as heat and friction, throwing it all away. Then comes the truly expensive part: getting it moving again. Accelerating a stalled 15,000-ton train from a dead stop is the single most fuel-hungry thing a locomotive will ever do. To break that much mass out of standstill, the diesel engines have to run at full throttle, burning up to 250 extra gallons of fuel just to claw back up to track speed. That's the equivalent of pouring out about 5 bathtubs full of diesel in a matter of minutes. Gone, just to undo a single stop. And that's before you count the fuel each locomotive burns simply idling while it sits, or the most valuable resource of all, track space. On a busy single-track main line, a stop train is a roadblock, and a single 30-minute delay can ripple backward through the whole network, forcing other trains to slow down or pull onto sidings miles away. Dispatchers measure that mainline time in thousands of dollars an hour, which means one badly placed stop can quietly eat the entire profit of the run. When you put real numbers to it, the decision makes itself. Building and maintaining a dedicated fueling station can cost something like $10 million. And every time a train stops at one, you are spending on crew time and yard delay before you even count the fuel penalty, the idle burn in those 250 gallons to get rolling again. On a busy corridor, an hour of a train's time can be worth thousands of dollars once you account for everything it's holding up behind it. Now compare that to a direct-to-locomotive truck delivery, which costs only around $30 or $40 in labor and wear per event. While the locomotive keeps running, the train stays together, and the fuel pours in at over 200 gallons per minute. Line those two columns up side by side and the verdict is overwhelming. The fuel stop was never really about the fuel at all. It was always about the staggering cost of breaking the train's momentum, and the cheapest fuel stop is the one you simply never make. This obsession isn't just about convenience, either. Fuel is one of the biggest financial forces a railroad deals with. For a major railroad, diesel can account for something like 10 to 15% of all operating costs, and the industry collectively burns through an almost unimaginable amount of it every single month. That's why railroads treat every fraction of a percent of fuel efficiency as an arms race. But it also creates a strange twist. Carrying all that fuel isn't free either. 5,000 gallons of diesel weighs something like 18 tons, so a 3-unit consist is dragging 50-plus tons of dead weight that earns no revenue, quietly burning extra fuel just to haul its own fuel over every mountain pass. Range, weight, spill risk, theft, regulation, Every extra mile of independence carries a real physical price, and railroads are constantly balancing all of it. To squeeze the absolute most out of every gallon, the industry leans hard on smart technology. Onboard software acts like an intelligent cruise control, constantly reading the train's weight, length, and the grade of the track ahead to manage the throttle and braking far more smoothly and consistently than a human ever could, quietly saving fuel on every single trip. Other systems automatically shut a locomotive's engine down when it's been sitting idle too long and restart it the moment it's actually needed, stopping thousands of gallons from vanishing into thin air for no reason. None of these tools rewrite the basic fueling model. They don't get rid of the tank or the trucks, but they stretch every drop further, and across a fleet of hundreds of locomotives, those small percentages add up to millions of gallons saved. And behind all the engineering and economics, there are people making this happen in real time. In rain, snow, and sub-zero wind, mobile fuel crews work 12-hour shifts, climbing onto idling locomotives during those brief 15-minute pauses to wrestle heavy hoses into place and pump diesel at full speed before the clock runs out. To them, a stationary train isn't resting. It's a countdown. And in distant control centers, dispatchers treat an unplanned stop as something close to a failure, a crack in a timetable they've engineered to the minute, because they and the engineers in the cab all understand the same hard truth about the cost of stopping and restarting a mile of loaded steel. From the ground crews to the dispatchers, the entire culture of the railroad is built around one unyielding rule: keep the tonnage rolling. So what about the future? Battery electric locomotives are starting to appear, carrying enormous battery packs and even recapturing energy as they break downhill, running the traction motors in reverse to feed power back into the cells. It's genuinely promising technology. But today's batteries hold far less energy for their weight than diesel does, so a heavy-haul electric unit might only manage around 90 miles before it needs to recharge. And recharging means expensive charging stations and stationary downtime, the very kind of stopping railroads have spent 100 years trying to eliminate. For that reason, the diesel fleet and its continent-spanning web of fuel trucks and yard stations will be around for decades yet, most likely in hybrid trains, where diesel and battery units run side by side. But whether the power comes from a diesel tank or a lithium cell, the guiding principle never changes. Keep the train moving, so the next time you watch a mile-long freight thunder past a crossing, remember that it may not stop for fuel again for hundreds of miles, not because it doesn't need diesel, but because an entire industry has spent a century making sure the fill-up happens invisibly, folded into a stop that had to occur anyway. A pool-sized tank, near-frictionless steel wheels, fuel trucks that chase the train down, and the punishing physics of stopping 10,000 tons. Together they turn refueling from an interruption into something you'd never even notice. In the end, it all comes back to that one iron law of the rails: the cheapest fuel stop is the one you never make. If this changed the way you see those endless freight trains rolling past, do me a favor and hit subscribe. It really does help the channel keep making these deep dives. And I'd love to know in the comments, what's the longest freight train you've ever been stuck waiting on at a crossing? Drop it below, and I'll see you in the next one.